this class, I wanted to talk about memory in the ESPs. So ideally there would be like a whole lab about like memory, but unfortunately there's just not enough time in the quarter. But when dealing with embedded systems, what's kind of interesting is you're dealing with such small amounts of memory usually that you actually need to somewhat be concerned with the amount of memory that you're allocating and working with. Also, your processor is really slow, so if you need to like copy large amounts of data on and off your memory, it's generally not going to be a great idea. So you have to be much more careful with your memory. And if you're careful with your memory, you also just maybe you're just wondering like how memory is handled in general. So does anyone know how much RAM the ESP32 has? So if you look up, actually, is anyone want to Google it who has a laptop out? So the ESP-C3 amount of RAM, or RAM size. Can you find it? Okay, yeah.
I got 4 megabits.
4 megabits, 16 megabits. I think it's less than a megabyte at least. Yeah, so I think it's about, like 400 kilobytes. I think that's what I found when looking at it, which is like absurdly small, right? Like on my laptop right here, like this has 32 gigabytes, so 32 billion bytes. This has like 400,000 bytes, so significantly less memory. But if we now wanted to consider how pointers now work, right? On most computers we deal with 64-bit pointers and maybe 32-bit pointers. But how can it be that we only have 400 kilobytes of RAM on our ESP32, but our pointer size is still 32 bytes? Or 32 bits. So let me quickly do that math for you. So So if we have 400 kilobytes of data, what bit width would we need in order to represent the maximum possible address in a 400 kilobyte address space? That makes sense. What would our address size need to be in order to represent the last value in our big memory array? It would probably be the log base 2, right, of 400 kilobytes. Have you seen this before, right? So this will now give us 400 kilobytes. This would give us the address width, which I think, anyone want to check this? I think it's 19 bits. Okay, yeah, so that means that if we now have our ESP32, and 32 denotes the pointer size, so the address width. So our ESP uses 32-bit pointers, but our memory only needs actually 19 bits of address space, which is funny. So, but our RAM only has 19-bit addresses. Okay, so this is interesting, right? Because what if now in our ESP we want to access memory that is outside of this 19-bit address space? So for example, let's say now that our ESP, actually, I'm gonna pull up this example. I started coding it up. Okay, cool. So here you can see, so here's just the hello world example, pretty good. And you can see what I'm doing is I'm taking this integer pointer and I'm finding the size of this address width. So we would imagine, right, that this should probably be 32 bits because that's just what the ESP expects. And then here we can see that the max address, I'm just calculating that as the address width, and I'm shifting 1 and then subtracting 1, and then that gives us now our max address. And so if we now go and run this, then we should see now the correct maximum address that we can represent. And so I think it'll be like really fun to just kind of play around with this and like see like how we can like I don't know, see if we can make the ESP kind of bend to our will so that we can really understand what's happening inside the memory. So I'm gonna quickly hook up the ESP. Okay, so now it is building this hello world example. So we should see like 32 bits. But okay, while we're waiting for this, I want you to like lightly kind of discuss with the person next to you, like why is it that we will see 32 bits here for our address width, even though our ESP only has 19 like bits of address width on its actual like RAM. Like the RAM itself only has like 19 bits of address space, but for some reason we are still able to have 32-bit pointers. So let's see. So cool. So in fact, yeah, we can see that our address width is 32. And then it says like this is our maximum address, assuming that we did actually have like the full like address space available to us. But okay, how is it now that we've sat with it for a second? Can anyone explain to me how we can only have like 400 kilobytes of RAM, but our pointer size can be 32? Okay. Yeah. Using memory somewhere else on the chip? Actually, no. Yeah, there is no other memory. Like, there's not an extra like gigabyte just kind of lying around somewhere. Yeah. Sure. I think there is some sort of like kind of swapping around that's happening. Yeah. Okay. So let's do another kind of example. So maybe we just Googled something completely incorrect. Maybe when we Googled the memory size, that was actually wrong, and we actually maybe do have like this total amount of like bytes on our ESP. Like probably not. This is a lot of bytes, but it's possible that maybe we do. So let's go and test. And I actually have kind of pre-prepared this little code snippet here, and so you can see. Yeah, so what you can see is I'm allocating just like a ton of memory. So I'm going from I until like the number of allocations possible. So you can see I'm like going all the way up until the maximum address, and I just keep allocating. And then we probably won't encounter this, but like if we ever encounter an error for some reason, then we go and print out that there's an error allocating. Okay, so let's go and test this out. Hopefully, we don't get any errors. Now we can just see like that we do in fact just allocate all that memory. So let's see. Okay, any thoughts on what we will see? So if I just keep allocating, any thoughts? Will it completely will it end up allocating all of this memory, or will it now error out? Okay, cool. So good. Okay, so you can see that it did, in fact, it started running the for loop. So it started allocating memory. So you can see it initially allocated, it looks like 4096, then it allocated some more. But then, after a while, then look at what happened. It looks like it did actually get an error. And can we see what address it around what address it got the error at? What is that? Does that look somewhat familiar? So this is around 300,000 bytes, which is kind of close to 400,000 bytes. So this is around 4 kilobits. So around 400 kilobytes. So it does in fact look like we only have about 4,000, it looks like we only have around 400 kilobytes total on our machine. And then the second that we fill up all of that memory, we do start getting errors. Okay, unfortunate. So there's no extra memory. Genuinely, even though it looks like to our program at first, it looks like, if I didn't go and Google ahead of time how much memory the ESP had, to my perspective, I would have really had no idea how much memory we had in total. So this is the concept of virtual memory. Have you heard of virtual memory before? Operating systems class? Yeah. So this is a really great example. One of the reasons because the ESP has so little memory, so it's actually really fun to kind of dig in. But you can see that it's very easy to use up all of the memory and see that the amount of memory that it has is very, very different from the total amount of address space that that our program looks like it has access to. So I'm going to quickly switch to my iPad, and I'll show you exactly what's kind of happening. All right, okay. So this is what we currently have right now. So you can see our physical memory is like it's quite small. It only goes up to, this I believe is 19 bits right here. And then this is our virtual address space. So this you can think of as like the user program. So the user program like effectively just kind of like imagines that it has this full 32-bit address space, when in truth our physical address space is actually much smaller. And that means that if I wanted to like actually go and start like filling up the virtual memory space, like as what the program did. So as I started filling it up, what happens is this actually gets mapped onto the physical memory using a kind of a special algorithm. So it's possible that maybe like this section right here is actually mapped to like the entire kind of physical memory. Okay, and but our user program, the like great kind of thing about virtual memory is our user program won't actually know that we kind of have a limited amount of memory. Like from its perspective, it thinks that we have a fully unlimited amount of memory. And it's only until finally when we kind of reach an error. It's when we fill up our physical memory that now we get like an error allocating, and now our operating system will send out an error that's like, hey, like, you know, malloc failed, so therefore, like, yeah, please like stop allocating so much memory. Otherwise, the user like totally expects that we have like basically infinite amount of memory. Yeah, sure, cool. So I want to like briefly kind of walk through the algorithm. I think you've maybe learned about virtual memory in the past, so I'll go kind of quick. But okay. Yeah, so let's say. So let's ignore kind of memory addresses for just a second and think about things in terms of just like, we call them pages. So let's now imagine that maybe like a page is maybe like a single like 4096 size block. So here we would call this maybe like, this is like page 0, page 1, page 2, and page 3. Okay, so this is our physical address space. And then our virtual memory, will most likely be like emulated to be much larger. So maybe this has like 8 kind of quadrants in it. Okay, and the idea is that any time that we put something inside of our virtual memory space, so anytime the user tries to put anything inside of the address space, instead what will actually happen is we will determine some sort of mapping to put it into physical memory. So what I'd like to do is like start kind of from the beginning. I'm noticing that not everyone is, I think I've lost some people, so I'd like to kind of recollect this because this is a really interesting kind of algorithm. And we can go really deep into it because like of RISC-V, because it's open source. So, okay. The first thing that happens when you turn on the ESP is it will run something called a bootloader. Any guesses for what a bootloader does? What is a bootloader, roughly? Yeah.
So it's what takes all the stuff in the non-volatile memory specifically.
Possibly. So a bootloader is a application that runs on the ESP or runs on whatever computer that effectively just kind of boots your operating system and boots all of the programs and kind of gets everything set up. So the first thing that happens when you run the ESP is it runs the bootloader. And what the bootloader will do immediately afterwards is then it will go and run whatever user program you have, and it will tell the user program about a virtual memory space. And the way that it does that is first it will establish something called a page table. So your bootloader, the first thing it does is it will pick one of these pages inside of the physical memory and it will establish it as the kind of page table. So what you can call this maybe the page table. So we can say that in the physical memory, and this is only accessible to the kernel itself, to the operating system, what we can do is just make like a we can list out all of the different like physical kind of pages in our physical memory. And what we do is then we give this like kind of table to the user program. And now when the user program maybe wants to go and fill out maybe like this cell right here. Maybe the user program wants to access something in this data, in this region of the virtual memory. Then what it will do is the operating system will realize like, oh, okay, so page table or page 012. So page 2 looks like is trying to be accessed right now. So therefore, I'm going to go and put this now inside of our physical memory, maybe at this spot. So now the operating system has now managed this, and now you can see that it is now mapped that we say that page or virtual like page 2, so this is 012, now maps to physical page 1. And later, if I now want to access memory like way outside of this region, maybe I want to access something way over here, which is like very clearly like maybe this is like some huge address right here. Then like that's totally fine. Now we can go and map it. Here, I'll make it a different color. Now what we can do is map it maybe over here. Okay, and if we go and map this address over here, how would we go and update this page table to now accompany this this like red mapping that I just drew? How would we change this? What was that?
Include a new entry.
Yeah, include the new entry, and what would it look like?
Virtual 6 to physical 2.
Yeah, exactly. Cool. So this looks like this is page table like 6. So we would say like virtual 6 now maps to physical 2. Great, cool. And yeah, okay, so question now, okay, who manages the page table over here? Like, did you have to write any like code that used page tables or anything? Like when you write ESP code or when you write like, I don't know, any code on your computer? Do you manage this? No. So the operating system, kind of behind the scenes, will manage this page table for you and will give the illusion to you, the coder. It gives the illusion that you almost have like unlimited amount of memory. It gives the illusion that you have full 32-bit pointers, when in truth you only have like kind of this small amount. Yeah. Okay, and now if maybe there was another program, maybe, and actually let's say maybe we go and, let's say now we go and like swap out this like memory. Now let's say maybe we don't want to put this inside of physical memory anymore. Maybe whatever, deload all of this. So let's imagine that this is the only thing that our ESP is doing, is maybe it's just loading a single page to physical memory. Okay. Now let's say that we have another program that is also trying to be run at the same time. Imagine this. Okay, so this program is now being run. What now needs to happen when another program comes along? What does the operating system need to do? Okay, it's a two-step process. Yeah. Absolutely, yeah. So this is like an example of how the virtual memory is like mapped to the physical memory. Notice though that this virtual memory space is completely specific to our program, like to the first program that's being run. But when we want to run now a second program, we also want to give that second program the illusion that they have unlimited memory. So if we ever want to run a second program, what we need to do is make a whole nother page table. A whole nother virtual memory space and page table. So this is maybe like virtual memory 2. Maybe this is virtual memory 1. So this is the first program's virtual memory space, and then this is the second program's virtual memory space. Okay. How do we now establish that this virtual memory space, how do we establish this from the perspective of the operating system and whatnot? What's the thing that we need to do? Okay, yeah?
Give it some physical memory.
Exactly, we need to give it physical memory. What is the most important thing that we start doing when we create a virtual memory space, though? What was that? Yeah, page table, yeah. So that is the main thing. So every single program that runs on your computer will have its own virtual memory, which effectively just means there's a unique page table for every program that's running. So we can call that this is whatever. This is program 1. And then maybe down here, let's go and put, I don't know, maybe we want to allocate from the exact same address. Maybe we say that still, we want to put, we still want to access the virtual page table too. But now we can go and maybe put it in here. I'll go and color code that. So there we go. Cool. Okay. So in that case, then what would our page table look like now if we were to fill it in this spot? Is this making sense? So remember, every program needs to have its own virtual memory space. And what all virtual memory space is effectively just a page table that tells you how to go from virtual memory into physical memory. So then what can we put right here to tell us how to go from virtual memory into physical memory? Yes, so this is the page table, and so what is the contents of the page table? Yeah, cool. Okay, I think I heard someone say it. So this would be now virtual page 2, again, because we're still in page number 2. But it would now be physical 3. Cool. So in this model, effectively the most number of programs that we could ever run simultaneously would probably be, I don't know, I guess it would be maybe 4 max, because you would be allowed 4 page tables, but then none of the 4 page tables could actually store any memory. So then maybe the max is actually only 3 page tables, and then you have 1 extra slot where the actual memory gets put in. Yeah.
Does the ESP32 do this, or does it have virtual memory?
The ESP does in fact use virtual memory. Yeah. Note though that this is all kind of done automatically for us through free RTOS. So the ESP IDF, when you compile your code, it automatically puts in a very basic bootloader that establishes this virtual memory for us. Yeah. Otherwise, what would happen is when we try to access memory outside of our address range, then we would get an error. But instead, if we go back to this example, so you can see I'm here, you can see I'm allocating memory at this address right here. But this address clearly is way past 19 bits of data. So this address is way outside of our physical address space. So therefore what we need is to have a virtual page table that then says actually yes, this is the physical address, or this is the virtual address, but it's actually mapped to a 19-bit physical address. It's mapped from the virtual address to the physical address. Yeah. Yeah. Yeah, sure. So the question was, where is the virtual memory stored in the chip? Well, sorry, yeah. So all virtual memory is effectively is it is just a page table that just tells the operating system basically anytime the user program, maybe so it exists in kind of this virtual address space. So it exists here, And what will happen is when it says like, hey, like operating system, I'd like to fetch some data at this address. Well, then what the operating system will do is behind the scenes, like secretly, it will actually just go and convert this, like, it'll convert the virtual address space that the user program thinks it's working on. It will go and convert that into the physical address space. And then it will go and like give out the data. So the virtual memory is actually that's completely stored in our physical memory. But the most important thing is the page table that just tells us like what the, like how to map it. I think it specifically tells the operating system like how to map the user addresses into the actual physical addresses. Yeah.
I guess my question was, is it our SRAM? Like,
Oh,
the ROM? Like,
I think I assumed that the ESP had some form of DDR in it. It's possible that it just has SRAM, but I think it has some amount of DDR. Oh, okay. Sure. It's probably stored in the SRAM, I guess. Yeah, maybe the ESP doesn't have any DDR. Yeah, sure. Cool. But this also means that now if we wanted to connect maybe like more physical memory later, that means that also now our user programs wouldn't need to change anything. So effectively, like the user program always expects that it will always have 32 like bit address sizes, no matter if we have like 10 bytes inside of our physical memory or whether we have like 10 terabytes in our physical memory. Yeah, so it's a very cool process. Okay, so the question now that you're all thinking right now, I'm sure, is you're like, well, you know, Ethan, like this sounds pretty cool, but how do I know that you're not lying to me? Like this seems kind of like a roundabout kind of algorithm. It's like, you know, maybe we could just bare metal, just write out everything into this physical memory, and yeah, maybe you're making it too complicated. So I guess the question is, how do we know that virtual memory is actually being used on the ESP? Okay, and what I'll tell you what a hint for that is the ESP uses RISC-V. Okay, what is probably, in my opinion, and hopefully in your opinion, what is probably the coolest part about RISC-V? Did you learn about RISC-V in your CSE121? Yeah, okay. So what's probably the coolest part about RISC-V? Yeah. It's open, yeah, it's open source. So there have been other RISC instruction sets. There have been other like extensible instruction sets. But RISC-V is great because what you can do is you can just Google the official like specification and documentation for RISC-V. Like if you wanted to look up the specification for x86, like if you wanted to like call up Intel and say like, hey, I want to give a lecture about virtual memory, like can you send over your documentation like of your instruction set? They would say like, oh yeah, no problem, just send over like $50,000 or something, and then we'll send you back the specification. And then they'll say also everyone in the room has to sign NDA or something. Completely different with RISC-V. With RISC-V, like anyone can just Google the specification, which is what I have pulled up right now, right here. So cool. So yeah, here is the official RISC-V instruction set architecture manual. Anyone looked through this before? Yeah, it's kind of cool. So yeah, kind of funny. I was actually hanging out with Andrew the other day, the creator of RISC-V. Yeah, by the way, just throwing that out there. Yeah, a nice guy. Yeah. We were standing on the beach looking at a sunset. Yeah. True story. Yeah. So okay. So here's the instruction set. It was for the LATCHUP conference, the Open Source Hardware Conference in Santa Barbara. Yeah. Yeah. Anyways, okay. So here's the latest release of the RISC-V instruction set, and then here is the PDF. And if we want, we can go and like search up virtual memory. And so in fact, the RISC-V instruction set has several mentions to virtual memory all throughout this manual. And if you were interested in implementing or like designing your own CPU that could use virtual memory, then all you need to do is just like read through this this documentation and you could figure it out. But basically there's a lot of like registers and random little things that you need to set in order to get it working. So what I just want to briefly kind of summarize how virtual memory and privileged modes and everything work. I'm assuming that at least maybe 5 of you in this room at some point will need to implement your own operating system. Like I can almost guarantee it. Like I've at this point have written, I think, 1.5 operating systems for things. Like it just so happens that you sometimes just need to get super deep into the weeds of your CPUs and looking at the control registers. So I want to just give a very brief overview of it. I'm certain that it's a crucial skill that at some point you will need to use. Okay, I want to briefly explain how to get virtual memory kind of working. So, okay, when your ESP initially turns on, so like I said, so it runs a bootloader, and that bootloader is effectively, it's run in something called machine mode. Okay, so a CPU, and this goes for basically every CPU, there are different modes that a CPU can be in, which effectively just will disable certain functionalities from the CPU. And the reason for this is because when you run a user program, potentially maybe like a virus or something, you don't want that user program to be able to control like everything on your computer. So therefore, when you turn on your computer at first, that is the only time that you have complete unlimited access to everything in your entire computer. So this is machine mode, so this is this is your bootloader. Okay. After machine mode is your CPU is running in machine mode, then what your CPU will do is it will go and now do a specific instruction, and let's see, do I remember the instruction name? It is, I guess it's M return to like return out of machine mode, and now this puts you into supervisor mode or kernel mode. So this is your kernel. So the kernel, that's basically like that's free RTOS or Linux or Mac OS. Like this is basically your operating system. Yeah, okay. And then inside of supervisor mode, this is where like virtual memory is generally like established. And then when we go and run a user program, what we then do is like, when we want to call a user program, what is it? It is, trying to remember, I should have written this down ahead of time. Yeah, okay, that I should have guessed. So this is supervisor return. Yeah, and when you run supervisor return, that is then what runs your user program. Okay, now question, if we wanted to enable virtual memory support, in your opinion, how should we kind of modify this diagram in order to kind of like show the order of like operations and say like, actually, yeah, go and like really quickly enable like a page table. So how would we modify this like kind of set of instructions or this diagram to show like that virtual memory is being enabled? Okay. Maybe I guess the question is, at what point do we set up our page tables and what does that look like? Okay, maybe go and tell the person next to you. How do we use this kind of flow to turn on virtual memory? Okay, yeah?
We're guessing in the supervisor.
Yeah, absolutely. Okay. So specifically, when in supervisor mode, or what would this kind of look like? Like what do you imagine a supervisor mode would do to enable virtual memory? Yeah?
Well, that'd be the thing that creates the page tables and virtual memory.
Okay, absolutely. So maybe we can, like right here, what we can do is expand out this diagram a little bit. So this will say like create page table. Okay. Anything else? Okay, yeah?
And then actually allocate the physical memory.
Sure. So I would say create page table. This is like, okay, we've now put a page table in physical memory. Maybe all the addresses are set up in the page table. But kind of the most important thing here is now we say, like, all right, the next time that we run sReturn, go and we would put this in a control, like, and we would put it in a control status register. So this would be control status registers. Yeah, so you'd run this command, and then you would put in now the address. So set So what you would then do is you would set the address of your page table. So this is kind of, this is how you establish virtual memory is in kernel mode. You create your page table, then you go and you set the address of the page table that you just created. So let me say that again. So when you go and like create a new user program, so the first thing you do is you create this, you create your page table right here. Then you go and say like, okay, now I'm going to jump into a user program. And by the way, this is the address of my page table. Okay, and there we go. So then that is how we finally are able to run in user mode. And the user mode is able to recognize that we have virtual memory now. Yeah. Congratulations. We now understand. So I'm going to briefly pull up an operating system bootloader that I wrote a while ago. Okay, and I won't go super in-depth in the code, but I'll just kind of briefly walk through it. So here we can see the bootloader, and what I'm doing is I'm initializing all of the page table entries. Actually, this is using something called a hierarchical page table, which is actually what RISC-V does. So if you actually start reading the documentation, it'll be called a hierarchical page table, which I won't get into, but okay, cool. So I'm setting up the hierarchical page table right here. And then here I'm setting up the physical memory protections. So this is important because we don't want our user space to be able to access like every bit of memory on our entire computer. So what I'm saying is I'm specifically allowing very specific registers, very specific addresses that the user is allowed to access. So okay, so I'm setting up the protections, and then you can see now I go into kernel mode, and so this is the last time that anyone would ever kind of be in your bootloader. This is it's basically just setting up all of the kind of the basic kind of just functionalities of your machine. Okay, then here's my operating system. So here's where now I enable virtual memory, and you can see that I'm setting up more kind of page table stuff. Then here I go and I set my control status registers, and I fill out and I'm enabling. You can look up in the documentation why I'm like setting bit 18 here, but I guess this sets the page table entry to S mode. And then finally, as I scroll down, you can see it then goes and runs sReturn. And now this will allow us to jump to this user program. And this just models some sort of like basic thing where it just loads in some number and then exits. So cool. That is kind of virtual memory in a nutshell. And I just want to kind of throw out there that you can this is not like an operating systems class. There is no assignment covering operating systems of the ESP, but going into the like RISC-V manual and like learning about virtual memory and learning about privileged modes and physical memories is honestly like pretty fun, pretty exciting, and also something that I'm guessing at least like five of you in this room at some point will need to like dig into. So now you have like the slightest bit of of introduction and understanding of how this kind of all works. So when you go and get that job interview question, that's like, actually, you know, we really need someone to be like the operating system like lead on this next project, like to kind of have an understanding of how to get started with that. You'd be like, oh yeah, actually, like roughly know how machine mode goes to supervisor mode, which goes to user mode, and yeah, establishing page table entries. So cool. Okay, I didn't really stop for any questions at any point. Anyone have any like burning questions now that I've kind of gone over kind of roughly what the ESP is doing, like right at startup before it's eventually thrown onto us, where we just have our nice 32-bit pointers and don't need to worry about anything. Yeah.
I have a sort of related question.
Yeah.
Say we just bought like a random, say, Snapdragon CPU. Would
Yes.
we have to enable all this ourselves, or would it come with the CPU already encoded?
Oh, yeah. So if you go out and buy yeah, sure. Maybe I don't fully understand the question.
Say that
yeah.
you wanted to make like a custom OS for some product,
and
and then you bought a pre-made CPU.
Yeah.
Would you then have to do this stuff, or would it come installed on the CPU?
Yeah, exactly. Yeah. So the question is, yeah, if you go out and buy a CPU, maybe you want to now make everything else like from scratch. Maybe you want to go and make your own Linux like version. Maybe not distribution, but I mean like your own operating system from scratch. Then yeah, what you would need to do is basically write out exactly this program right here. So what this program actually is, this os.s file, this actually is, this is a bootloader I wrote, not for a Snapdragon CPU, but for a different CPU called CVA6. It's a very common kind of embedded system that is capable of running Linux. It's fully open source. Yes, and what I had to do in order to get the CPU working at all is I needed to give it this program to establish all of the virtual memory and everything. Yeah, absolutely. Yeah, every single CPU that you like inside of your computer and or even the Raspberry Pi, the Raspberry Pi and the ESP32, like everything has to have some sort of like basic bootloader on it. Yeah, and you would need to go into the documentation to figure out exactly what like random registers are being set and stuff. Yeah. Yeah, absolutely. Yeah.
So would you consider specific bias CPU that has like ARM architecture or just like the
Yeah, good point. Yeah. So here's What was that?
Like you couldn't just buy any CPU.
You could buy any CPU because basically all CPUs support some sort of virtual address, like have some sort of virtual addressing support. There are a few like embedded CPUs that don't have any like physical memory protections, but honestly those are very rare. Like most of the time you can choose not to use virtual memory, but like maybe if you wrote like assembly programs in your CSE120, maybe you didn't enable virtual memory. You probably did not, but you had the opportunity to if you wanted. Basically every CPU allows virtual memory. Yeah.
I meant that you would have to buy a license to like use the instruction set or something else. Like not every CPU works with an open source instruction set like this. Is that?
So every CPU has a different instruction set. Yeah, so for the RISC-V instruction set, this code would work, but like actually, yeah, so for Linux actually, you can go into the bootloaders of Linux and you can see that every different operating system, every different architecture has a different bootloader. And you can actually go into the Linux source code and you can find the RISC-V bootloader, or you can go and find the x86 bootloader, or you can find the ARM bootloader. The code itself is not proprietary. Like you can look at that bootloader fine. What is proprietary is the documentation. So you're not actually allowed to like publish how to use the processor, but you can publish code that happens to work on the processor. Yeah. I don't know if that answers the question.
That was more like it. Like,
Okay.
Yeah, like I couldn't go and buy anything and then program it myself.
You could buy anything and program it yourself. The issue is that you probably don't know how to program it. Yeah. Yeah, it's like a weird thing. Actually, yeah, there's a... Well, right, so Ghidra is for reverse engineering I would say not really for virtual memory. Geetra is good at reverse engineering like C binaries back into C, but not really for determining what control status registers you need to set inside your CPU to enable like the certain functionalities that you want. Yeah. Potentially. Yeah.
This time I wonder if when you wrote this like bootloader,
Yeah.
did you have to like program how the OS like handled anti-loading, or was that like something, or was that from someone else?
So absolutely. So in this case, so it's all kind of hard coded, and you can see that it's actually kind of boring because the user program is just this single thing right here, and I'm just kind of hard coding this program into the memory. If I wanted to have multi-threading, then that would be like very kind of, it would be somewhat straightforward. Basically, I would just have multiple user programs all just kind of running, and when a user program finishes, then it like knows to run like another user program after that. Yeah, I'm not sure if I totally understand the question, but basically like to enable multi-threading, it's generally pretty straightforward in operating systems. You just choose to run like more than one like process at a time. Utilizing more than one core though is tricky. I'm not sure if that was your question.
Yeah, I'm not asking that. Well, because I was just thinking like, because the free RTOS
Mhm.
is part of the bootloader.
Yeah.
That's like a thread library.
Uh-huh.
So like, I guess that's where.
Oh, sure.
I was-
Yeah, so free RTOS. I guess roughly, I'll just spend a minute on this. But yeah, basically what you have is you have this process queue. So all operating systems, so OSs have a process queue filled with like tasks to run. And a user program can request for a program to be added to the process queue. So that every time you run like X task create, you basically just add it onto the process queue. Then it's up to the operating system how to actually like pull things off of the process queue and actually handle each of the processes. Yeah, it could be that it basically just runs a process, waits for it to finish. Once it's finished, it moves on to the next one, waits for that one to finish, moves on to the next one. You could do that. Most operating systems will kind of just do like a random like thing where it'll run something for like a millisecond, then it'll stop running it, and then it'll run something else for a millisecond, stop running that, run something else for a millisecond. That's what operating systems generally do, is they just kind of pull things off the process queue in like a random order. Yeah, so that's what multi-threading kind of is that a user can put a bunch of things onto the task, onto the process queue, and then allows the operating system to determine like kind of the best order to run all of those processes. Yeah. So in what I would need to do here is have some way to, I would need to have like basically some while loop, and I would need to have something that like runs all the things in my process queue. But I don't have a process queue because it's just one single program. Yeah. Good question. Sure. I think like I'm a big fan of going deeper, and I'm a big like architecture guy, so it's fun. Okay. So on Wednesday, we will return back with, I'll talk about lab 5, lab 6, whatever the next lab. I think I'll start talking about lab 6. Lab 6 is due next Friday, so please already start looking at that. I think it can be a little bit tricky, so yeah, definitely get started. Cool, okay, see you on Wednesday.